All right, welcome back. Today we're going to be completing part D of homework 2 for separations. Now, among all of the parts, this part is definitely the most integrated with the last part when compared to any of the other homeworks. It's essentially the same problem, and we're utilizing the NRTL, bubble T, do T, all of that we previously derived. And this work in particular that we have sitting in front of us, if you go through about halfway through my part C video, you'll see me explain and go through how we found this code here. But what's essentially happening is right here, we're trying to come up with a good initial guess for our duty NRTL by looking at the ideal condition, similar to how we did it in homework 1 for separations, where we were finding a duty and a duty. We're essentially using that same code in order to create an initial guess for our NRTL duty that we're finding down here. And then I went through a little bit of just starting us out, getting us our initial temperature and pressure, as well as putting that into a vector. So continuing on from there, I think we are good to finish this code up and go through our flash calculation that we have previously done, but this time with the NRTL derived dew temperature. So let's go ahead and get started with that. All right, now we're gonna go ahead and define our f fruit. So we're just gonna say define fruit as a function of our vector v, and then we are going to say that t is going to equal v at first number in that array, and then we're going to say that x is going to be the second one, as that's what we've established up above there. So colon, and then we are going to return np.r x times r dot gamma, or NRTL underscore gamma times r dot, oh, I need to put this at x and t. And then I'm going to say r dot pvap at our temperature, all divided by p minus y. I think that should be all good. And then we need to do np dot sum x minus 1. Fantastic. And now we can do our SciPy optimized, find our root for our duty. So we're going to say SciPy.optimize. I did not spell that right. Optimize dot. I need to find this as our result. Say our result equals SciPy.optimize.root of our f root and our v. Oh, it's our initial guess dot x, and we can finally pop out and return our result. First variable, so we're going to return as at 0, and then our result at 1. Fantastic. Shift enter. I always forget that comma. Man, really struggling with this. Right. Shift enter. Oh, worked this time. All right. And we can go ahead and do that flash calculation that we did have done in a previous homework, just with our NRTL variables we have now. So let's go ahead and get started with that. So we're going to define our flash PT as a function of our Z, our P, our T, our feed composition, our pressure and temperature, as well as that niter that previously we're going to set it to 100, and our tolerance, which we're going to set equal to 1 e minus 6. Let's get in here. So we're going to say that our dew point and our x dew are going to equal dew p, p and RTL, at our hold on. Wait, which 7? Sorry about that. Somehow I accidentally deleted my line of code. Just click something on the keyboard. We're moving on. We are going to define our bubble P and our Y bubble as a function of bubble P NRTL, bubble P underscore NRTL, again at our Z and our T. And then we're going to need to do that thing to kick us out if we're ever not in a vapor liquid equilibrium system, if we have all liquid or all vapor. So we're going to say that if P is greater than BP, we need to, I need to put my if statement in here. If P is greater than BP, we need to return all liquid. And then if P is less than dP, we need to go ahead and return all vapor. So that'll kick us out if we're ever not in our vapor liquid equilibrium before we go into our flashpoint calculation. And we did something similar to that in one of our last homework parts, if you remember. So moving on. Now, if we remember, we had a really good initial guess for our phi, which is what we're actually going to find. Our initial guess was our P minus our BP, our pressure minus our bubble pressure, divided by our dew pressure minus our bubble pressure. And as we discussed previously, this is because you're looking at how much, because your dew pressure minus your bubble pressure, that's essentially the range of your vapor liquid equilibrium. So we're looking at how far along we are in that range, if that makes sense. So the closer P is to dP, the more liquid that we're going to have in the system, making it a good estimate of phi for us. So that's going to be our initial guess. And then moving on, we're going to say that our x is going to equal our initial guess for phi times our x dew from up above minus z all plus z from our overall equation. And then from there, we are going to say, have our for loop. So we're going to say for I in range niter, I need my colon yet again. We're going to say that I'm going to say that K equals R dot and RTL underscore gamma at our X and our T times our R dot evap, our saturation vapor pressure at our temperature, all divided by B. All right. Now we need another fruit function, so let's define our fruit as a function of phi, as that's what we're trying to find is our phi here. And we are going to return our Jackson NumPy sum of k minus 1 over 1 plus phi, 1 plus phi times k minus 1. Fantastic. Then we're going to multiply that entire expression there by z. All my parentheses, right? Yes, that's all good. And then since we're going to be later using the Newton method to find the root of this, we're going to need the derivative of our f root as well. So to do that, we're going to do, as we've done previously, Jax dot gradient, or first we need to say that f root prime is going to equal Jax dot grad of our f root. And that'll give us our f root prime, our derivative, so that we can now go ahead and do our SciPy optimize with this f root prime. So now we can say that our phi is going to equal SciPy dot optimize dot root scalar going from f root starting at our initial guess of our x not equals phi, or f prime is going to be equal f root prime, and then our method is once again our Newton method dot root. Fantastic. And now we're going to update our x new. So our x new is going to equal our z all divided by the same denominator up here, our 1 plus phi times k minus 1. And all of this, I'm not going into deeper depth with this because we already went through our huge derivation up on the board to find our Rashford-Rice, because that's the point of this, is to apply the Rashford-Rice using our NRTL calculations. But I'm pulling all of this just from our derivation up here of the Rashford-Rice equilibrium. So that's why I'm not going any deeper with the explanation here. It would be kind of redundant based off of the earlier iterations of these homeworks. So anyway, continuing on, we got 1 plus phi times k minus 1 for our x new. We're going to use this to kick us out once we hit our tolerance. So we're going to say if, hold on, we're going to say that if numpy dot lin alg dot norm, I think x new minus x is less than our tolerance, then we are going to break our function. And then we're going to set our x equal to our x new so that we can have that all updated. We can break out of our big old loop here. And then we're going to solve for our y after we break out of most of this. I'm still, okay, here we go. Our y is going to equal our k times our x. And then finally, we're going to return our phi, x, and y. Phi, x, y. Shift enter. I knew it. I knew it. All right. Where is our problem here? Unindent. Oh no. Move all these back a little bit. Too many indents. Too many indents. If x equals x new, return. Now I don't want to back that out. Just gonna shift enter and see if this works. All right, another indent. Why the hell's the problem here? I fix now? Man, all right, well, I'm just gonna have the AI fix this because I'm just kind of wasting everybody's time here. With all these indents. Holy crap, what all did it do? Oh, well, I guess there's a lot of spelling errors in there, but that's all right. Look over this. Everything else is all right. Fantastic. All right, now that we've gone through all of that craziness, we can finally get at the root of our problem here, which is to perform our Radford Rice calculation at a given concentration. So let's go ahead and plug our problem values into this. So we know that for our flash PT and RTL, and we're looking at, for the two components, we're starting at 0.25 and 0.75 as our initial feed concentrations. I believe we're at 1 bar, so we're going to say 1E5. Is that how? Yep, CPT. And then we are at 360 Kelvin. So, hold. Oop, I need to put parentheses around this, of course. Get that fixed. Shift enter. NP is not default. What? All right, well, let's just ask the AI what's going on here. What is happening? Oh, well, it's certainly helpful. We'll go ahead and this might take a second. We'll run all. Once we get to the end of this, hopefully we'll have all of our humongous file ran through. Burning through Google's GPUs. There we go. There we go. And look at that. Let me check over here, make sure that's all right. Yep, it's all good. So we've successfully performed our flash calculation using our NRTL for our activity coefficients. And I believe that is the end of part D for homework 2 for separations. See you in the next one.